energy sources we have today. We need something that at least competes with the promise of new fission technologies and emerging fusion technologies, and that gets us to the idea of what is the potential here for uh, replacing these ideas of fission and fusion with a low energy nuclear reaction. And if you think about what's being done in Europe with the ITER project, that's already in tens of billions of dollars and tens of countries contributing to the challenge. And the relatively small number of researchers in Leonard is where we're facing the problem. We can see that at 4,000 times the energy density of chemical energy and no greenhouse gases or hydrocarbon emissions pollution, Leonard holds an immense amount of promise, which is illustrated by this graphic. The upper right quadrant, the red dot shows you where Leonard can be estimated to deliver energy density compared to other energy sources. I'm not sure if this is big enough to read, but all those other colorful objects are other energy sources. So the last 30 years have seen development by different groups, starting with the original Pons and Fleischmann exhibition in Utah, and I think we didn't refer to Andrea Rossi here, but we'll get to that and his Italian efforts. I'm going to show a video now to give you a better explanation of what we've been talking about.
On March 23rd, 1989, two chemists stunned the world when they announced that they had achieved cold fusion in a laboratory. Martin Fleischmann, one of Britain's leading electrochemists, and his colleague Stanley Pons, then chairman of the University of Utah's chemistry department, reported that they were able to create a nuclear reaction at room temperature in a test tube. Since then, cold fusion has been replicated in hundreds of experiments in dozens of major laboratories, all reporting similar results under similar conditions. But what is cold fusion, and how do we know it is real? Cold fusion is a nuclear reaction that generates heat without burning chemical fuel. Cold fusion has reached temperatures and power density roughly as high as the core of a nuclear fission power reactor. Unlike most other nuclear reactions, it does not produce dangerous penetrating radiation because it consumes hydrogen in a nuclear process rather than a chemical process. The hydrogen generates millions of times more energy than the best chemical fuels, such as gasoline and paraffin. Hydrogen fuel is virtually free, and cold fusion devices are small, relatively simple, and inexpensive. They are self-contained, about the size, shape, and cost of a NiCad battery. They are nothing like gigantic nuclear power reactors, so the cost of the energy with cold fusion would be low. If researchers can learn to control cold fusion and make it occur on demand, it might become a practical source of energy, providing inexhaustible energy for billions of years. It would also eliminate the threat of global warming because it does not produce carbon dioxide. Most cold fusion reactors produce low heat, less than a watt, but a few have been much hotter. Here are 124 tests from various laboratories, grouped from high power to low. Only a few produced high power. Most produced less than 20 watts. In 1996, at Toyota's IMRA Research Lab in Europe, a series of reactors produced 30 to 100 watts, which was easy to detect. They continued to produce heat for weeks, far longer than any chemical device could. The core of the Toyota reactor was about the size of a birthday cake candle. A candle burning at 100 watts uses up all of the fuel in 7 minutes, whereas one of the Toyota devices ran at 100 watts continuously for 30 days. That's thousands of times longer than the candle. It produced thousands of times more energy than the best chemical fuel. So, if the tests were so promising and were able to achieve such high power density and run so long, why hasn't cold fusion become a practical source of energy? Because cold fusion reactions can only be replicated under rare conditions that are difficult to achieve, even for experts. It's like making a souffle. If you forget to put the egg whites in the souffle, even if you set the right temperature and do everything else correctly, you get no souffle. But when the right conditions are achieved, the reaction always turns on. SRI International and the Italian Agency for New Technology were able to get all of the critical factors just right and achieve the cold fusion reaction in several tests. It is not difficult for an expert to reach a ratio of hydrogen atoms to palladium atoms of about 60%. This takes a few days, but it isn't high enough to trigger a cold fusion effect. You have to go higher, and the higher you go, the harder it gets. But with the right kind of metal and good techniques, the amount of hydrogen in the metal gradually rises. When it reaches 90 atoms and other conditions are met, bingo, the cold fusion reaction turns on. This graph shows an exponential increase in power when the ratio of hydrogen atoms to palladium atoms exceeded 90%. A Toyota lab also saw the exponential increase above 90%. Hundreds of other researchers have seen the same effect. Another factor that makes the cold fusion effect turn on is electrical current density. The higher it gets, the more intense the cold fusion reaction becomes. When there is a reaction, that is. If there is no reaction in the first place, because, for example, the ratio of hydrogen to palladium doesn't get above 90%, raising the current does no good. We've learned a lot since the Fleischmann and Pons announcement in 1989, and we know what now must be done. But knowing how to do something doesn't make it easy. We have to learn more. With enough research, scientists may learn to control cold fusion and make it safe, reliable, and cost-effective. But it's going to take thousands of hours of research and millions of dollars of high-precision equipment. Basic research is expensive. However, if this pans out, it will reduce the cost of energy worldwide to practically zero, saving several $billions per day. This might happen as quickly as microcomputers replaced mainframe computers, or the speed at which the internet expanded after 1990. It can happen quickly because it requires no distribution infrastructure, and it calls for only a few changes to most core technology. In other words, a cold fusion-powered car would not need a gas station because you could run it for a year with a spoonful of fuel, costing a few cents. But that is information for another video, another day. To learn more about the potentially groundbreaking research surrounding cold fusion, please visit lenr.org. Thank you.
Okay, well, that's most of the presentation. There's some notes here I'd like you to look at about researchers that have been involved in the field. There are links embedded in the addendum, and you can follow some of these international researchers that are from Japan, China, Russia, India, and other places linked in this presentation. They'll be presented online.
Excellent.
Questions?
Yes. Maybe this might go to Charles and this might go to Frank because it's more on the science of it. But I mean, you can answer it too if you know the question or if you know the answer. So it's a chemical reaction, right, that occurs, and that chemical reaction creates, the excess heat that we need and that we want to use in practical terms to be able to you know create steam for an engine or to create heat for excess industrial excess heat. What are some of the more what are probably going to be the first implementations of this type of technology if it does break through? Would it be for the house, or would it be more for like to be, you know, implemented in old coal power plants that are no longer functional? Like, what are some of the what are some of your hypothetical guesses would be the best implementation of this technology?
I think initially it's probably likely that this will be you know residential heating or industrial heating for ambient temperature levels, and not so much process heat or distributed generation converted to electricity. And that's just because it's more likely that the first successful iterations will be something of that nature. Maybe Charles has a better idea on that too.
Asking me? It's Robert, when I talked to him, he thought he would sell it to the oil industry to use for manufacturing. I think it's a lot of people talk about just trying to make a boiler. So is that something you'd run in your house? Things that go in your house have to be approved. So I mean, if it were me, I would try to sell some sort of low-end product to people, just direct, like a generator. But it's the current systems require electrical input. I don't think they run by themselves, like they're not self-sustaining. So that's obviously if it's self-sustaining, you could just have a generator and you'd take it anywhere and it would just generate power. That would be ideal, but I've yet to see anything that can do that. I think it's like with a lot of these technologies, it's difficult to find markets for them when people already have alternatives. And I think it's going to really depend on the price point, and the manufacturing of it. I haven't seen, what I've seen so far, the manufacturing hasn't really been locked down yet. Like they don't really understand how to manufacture the cores systematically, which would suggest that these things could be quite expensive.
So along those lines, I noticed that at least in the video, they talked about being able to control on demand, how to control these reactors on demand. Has that issue been solved yet from the experiments that we've seen recently?
Nah, I don't think so. They don't know how to. You have to first. It's not so much a control issue as it is manufacturing the material. One has to manufacture like a little core, about, say maybe it's like this big, right? And you have to manufacture it, and it's not entirely clear how to do that. And there have been people who've made claims, and they've claimed, they've locked down the manufacture. If some people have claimed they figure out how to manufacture it, maybe the Clean Planet guys in Japan can do this. But getting this thing manufactured properly, it's very expensive. To manufacture a piece of nickel and to have the various kinds of metallic layers and to control its dielectric and electrical properties, it's a very expensive thing to do, and they don't really have control over it. Mm-hmm. So in terms of controlling the reaction, that's just power on, power off. That I think people have tried to figure out, but it's really the device, the material itself, which has been very challenging to manufacture.
Interesting. Frank, do you have any insights that you're allowed to share regarding Clean Planet and their implementation of their version of this?
Yeah, so their major partnership in terms of the manufacturing is a boiler company, right? So I don't know if this is an industrial boiler or something smaller scale, but that's the only thing I know. So that's publicly on their website.
Okay.
Yeah, about the manufacturing. So the one thing that seems to be known is that if you have pure nickel, they don't see this excess heat reaction occurring. But if it's doped with a few percentage of something else, like platinum or copper, then they see this effect. So they think by changing the grains in the metal. So the grains are like little subdomains. Like if you look at microscopically, you see like a little, literally a grain inside in the metal. And that seems to be a condition necessary to initiate this reaction. So, some people are theorizing, okay, well, maybe because you embed the energy chemically and that you're just releasing it. But it seems that there's actually quite a bit more energy, like 3 or 4 orders of magnitude higher than what you expect from a chemical reaction. So that's the observation that leads them to think that something's happening that's extraordinary.
I think you hit something important there, Frank, is that if I have a piece of nickel, pretend this is nickel, and I want to dope it, and I want to get a certain number of grain boundaries or cracks or vacancies in the material, how do you control that process? I mean, doping a semiconductor, they use nuclear, I mean, that's done with a nuclear reaction, right? And it's literally, they're transmuting lead to gold. I mean, so doping a material, getting the doping right and making sure you actually have the right kind of materials properties, that's in terms of manufacturing. I don't know what's going on in Japan. I mean, we certainly don't have, we're certainly not manufactured. We're not a smelt,
Yeah, I mean, that is really, doing that consistently is really, really hard.
Consistently.
Yeah, I mean, there's a product that was on the market several years ago. This whole, what do you call it? Yeah, these golf clubs that were highly, it would transfer all the
Caltech golf club?
Yeah, so they had this thing called the liquid metal, right? And it was, I think, 3 or 4 different metals, and they had to use like these exotic conditions to make it. But if you could get that consistency right, yeah, then you'd have all these new properties. But it was just like these, I think people spent like hundreds of millions of dollars developing it, but most of the applications never came to fruition, right? Because it was also for medical devices. It was also for like super hard needles. But yeah, I mean, most of it still hasn't been commercialized because it's been very difficult to manufacture it very consistently.
What is this golf club that you speak of? Where can I get one?
So I thought the main problem wasn't manufacturing, but seeing a net gain in energy. Has that been overcome? Sorry.
It's not net gain in energy. You're releasing energy at a nuclear level. So you're basically using E equals mc squared, right? So the basic concept in nuclear science is you're losing a little bit of mass because of a reaction, whether it's fusion or fission. The final product is just slightly less heavier than your beginning product. And that change in mass is the energy that you would see that's released in a nuclear reaction.
No, gotcha. I just thought there was something with, I remember listening to the Larry Forsley.
Nobody believes them, right? I'm sorry I interrupted you.
Oh, no problem. I just thought that there was some issue with the energy or electricity or whatever going in to spark the reaction was sometimes higher than the actual energy being created. So that's my misunderstanding.
No, I think the issue has been that, look, it's difficult to do this consistently. So that when you talk about measuring the heat, you have to demonstrate it to someone independently. I don't think there's been, it's not like someone is like Google, for example, they were not able to reproduce any of these heat experiments, despite having spent $10 million on it. So it's difficult to do reproducibly. And I think when they say they can't measure the heat, what they mean is that they can't get the experiment to work. Richard, I have a question for you on this. Look, one of the groups we are involved with is with Hagelstein and Mitchell Schwartz at MIT. And they have claimed for a very long time, and maybe since 2012 or earlier, that they are able to make this material through some sort of nanofabrication process and that they have a device called a nanor, and they've made things like they have made little devices that you can put on a computer board, like a resistor, but the resistor generates power. So you have like a computer board that doesn't need a battery. They've claimed to be able to make certain kinds of Stirling motors, which are, you don't know, very, very high performance motors. Like Stirling motors, what you have inside that, what's that thing the thing you ride around on, you see people in the park, you don't want to walk.
Oh, the Segway?
The Segway, Stirling
Yeah,
motors
yeah.
in a Segway. It's a hyper efficient engine. What's going on with these guys? I mean, do they have something? Is it an IP issue? Because my impression, my understanding of what's going on from a business side is that they claim that they have reproducible manufacturing, but they are not moving forward because of the IP.
Yeah, without getting too into the details on that one, I especially don't like this. From all the evidence that I've seen, there are a couple of issues. The patent office always sees characters, right? Like it's a very thin line between brilliance and madness, and we see both sides of the line all the time. Like people that come in are brilliant, some people that come in are mad, and one of the issues, specifically in this case that you're asking of, is in the manner of which how he prosecutes the case. It's terrible. It's just really not competent type of filings. It's not competent type of arguments. And what happens is there is a confusion between the technical aspect of what Mitch Schwartz is working on compared to what's actually communicated on the filings that he is giving out. Best practice in this field, right? Like one of the things I did last year before the conference was actually visit the U.S. Patent Office and visit the technology center that actually works on these cases. And what I was talking to with the group was, hey, you know, there's this whole field here that's really there's a lot of momentum kind of coming up now. What are you guys going to do to accommodate your academic thinking on, you know, Leonard, these types of applications? There used to be a full stop. Whatever comes in, we're not going to allow it to go through. They've transitioned that where they used to have quote unquote special examiners who work on them that would just reject it to, oh, we're actually letting these cases go to the examiners and then having them examine them on the merits. But they're still very, very meticulous in how they prosecute these cases. Very, very well. But they had, what was the name of that professor from George GW, Frank?
David Nagel.
Yeah, David Nagel. So David Nagel came in to the patent office and actually gave a lecture on his findings. And that's actually, so every year there's one time a year that the patent office gives it's kind of like open mic for all different scientists who are innovating in the field to have them come in to do a lecture and talk about the field. David Nagel was the one lecturer that they had come in for that group. So it was interesting. And as I was looking through the classification of where these cases would be, you know, allowed, yeah, there was about 160% increase in allowed cases in that area at that time in the summertime. I think as I looked in November when Ms. Schwartz asked me to look again, it was about the same rate. You know, it's still increasing in allowances in that area, but the best way to practically tell you, there are 16 examiners who work in this field, and the amount of Leonard cases that they get is about, let's say, 25 cases a year. Each examiner works on about 125 cases a year. So when they receive one of these cases, it's sort of like out of the blue, like, oh, okay, I got a Leonard case, you know, and it becomes tricky. That's the thing, right? Like it becomes really tricky when you see a case that you're not used to and it comes across your desk. You know, the best way to combat that would be, you know, open communication. So in my case, it was sort of like having that conversation with them. It was like the first time someone from outside, you know, the patent office And outside of that formal teaching process, that someone came in to talk about this. It's like, oh, no one has come in here to lobby, or no one has come in here to talk to you guys about this. Like, no one has come here. So, you know, a lot of people like to say it's a conspiracy. The patent office likes to reject stuff. It's like, no, the patent office is like almost every other government bureaucracy. It's worse than a conspiracy. They're just scared. They're very scared of like getting on the news. And so like I've been on the news before for a patent case, and it wasn't great. You know, it was an argument between Apple and Qualcomm. Is one of my cases. Ultimately, my adjudication was correct, but no matter what, right? They have a lot of lawyers come in and sort of muddy up everything to make you look kind of bad. So,
can I kind of chime in on Charles's comment? I just want to say, you know, my background's in government procurement, and you know, for us in my role, we kind of support the scientists and the engineers, and you know, what Charles was saying is, you know, why don't we have like the you know, why aren't, you know, certain companies are able to do certain things with these the way they manufacture, right? And one thing I noticed in my background is, you know, working with the chemists and engineers is we're sourcing, you know, the technology or the services that are you know, we're sole sourcing it from other countries. And I'm, you know, like I'm looking at some of the things that we're doing. We're like doing polish, specific type of polished gratings or coatings for things like that. And I'm like, you know, why can't we do that here? And part of my job is like to look for that here in the U.S. And I'm thinking, well, you know, we have these scientists who are trying to do this science, but you know, they don't have the manufacturing capability to kind of support that. And I was thinking, like, why is that? Why is there a gap there? You know,
that's
like
probably more of a supply chain issue, right? Like why don't we manufacture more stuff here in general?
Yeah.
Well, I think we do manufacture. It's just they're not always in the same company. Like Boeing uses a group called Carpenter Technologies for their advanced alloy development, and Carpenter goes out and they acquire other companies if they don't have a specialty in something like titanium alloys. They'll go out and buy a company like Dynamet that has experience in smelting and refining titanium to support their Boeing contract. So, you know, there's the primary, you know, smelters, refiners, and there's the process people and the technology engineering group that does the, you know, final, you know, either forming or you know, casting or forging or machining. And even between those different groups, you have metallurgists that are not always familiar with the manufacturing process that goes into you know, creating a useful product from their alloy. So it's a complicated process, and I think a lot of the defense contractors have pretty much figured out how to work together.
Yeah, and especially Charles's case, right? He's talking about etching for nickel, for for a very specific. This is like, I know that we talk about Leonard a lot in our organization, so it's sort of like it dominates our conscience, but that's not the case for a lot of the rest of the world. Like there's a very few resources in this field to advance it, and we just happen to be one of the organizations that's one of the major player, or I wouldn't say player, but major supporters of this field. And so what you're witnessing is like, oh, this is science and engineering and all these things sort of meeting, but there's no political support, there's no like all this other support.
Yeah, I want to say, like, if the plan is to build a house, you're gonna need a hammer, you know, you're gonna need some nails. But if the only place you can get those are, like, you know, not within your reach, if you're only getting that from like in another country, then, you know, how are we able to like directly support our, you know, our efforts? You know, that's what we want to do, right?
Yeah, no, I totally see your point, but I would say specifically in this field, like at least if we're going to narrow the discussion to Leonard, um, all these other countries who are working on Leonard are probably in this, you know, in a similar boat to us. Like they're still trying to figure it out. Like, for you, right, your example of a house, you know how to build a house. You need all these different parts. These guys are like, they kind of know how to build a house, but they don't know if anyone's going to buy the house yet.
I mean, I think that, you know, you're working with materials that somebody else is making for you.
Yeah.
Or if you're trying to make them yourself, you know, if you were in a chemistry laboratory or a physics laboratory, you know, university environment, these are very, very expensive experiments to do, and to do things from scratch, to build a material like this. And, you know, you have to understand how to characterize the material. What are you looking for? And as Frank pointed out, there's still a lot of theoretical questions about what are the actual characteristics of the materials that you need to make this reaction happen. And I think some of the problem here is that, you know, without being able to specify that and measure it exactly and to know what you're getting, how do you know? You know, if you can't control the manufacturing process, you know, you have to do it before you get to the last stage of testing it. You don't want to be in a situation where you're buying cores on the market and then you put them in your device, and if they run, you can sell them. But, you know, 1 out of 100 works. It works for a week and then you burn it out. I mean, that's not a sustainable manufacturing engineering process. And to make it to that stage, you have to be able to go upstream and control, you know, maybe downstream is the way to say it, back in the supply cycle, and understand what is the thing you're actually what is it you're actually purchasing? What are you looking for? You know, a lot of the research being funded by Google is fundamental research. They have this research they've been funding in LENR, but a lot of it are things like, how do I characterize a material such that I take nickel and I load it with hydrogen, or I take palladium, which is by the way, palladium is quite expensive, right? You don't make cores out of palladium, it's so expensive. How do I load it with hydrogen and deuterium? How do I know that I've loaded it correctly? How do I measure and characterize it? Without that process, it's very hard to know whether you made the thing right or not. And so just if you ask somebody to take this, and if you have to do it yourself, you know, it's quite hard to do. So I mean, I think that was one of the things that came out very early we had a talk, Peter Hagelstein came and gave a talk here a few years ago, and he's talked about this for some time, that one of the most important things when they first tried to reproduce the Pons and Fleischmann experiments, they had this material, this cathode, and you have to load it with deuterium. How much? How much do you put in? You know, I mean, this was not specified in the experiment. So how would anyone possibly know? So that's just step one. Do you need 85%, 70%, 95%? Like basic things like this, which wasn't known during the initial experiment. They didn't even know that. So it's just, and so I think there's also a question, if you ask Mitch Schwartz, he would say, well, or Hagelstein, well, you need to have all these vacancies. Okay, but then let's say you make a powder. Well, the powder doesn't have necessarily, maybe it's not vacancies. Maybe it's what Frank said. Maybe it's dislocations. Those are two completely different things. Or are the vacancies a result of a phase change? It's like, you know, understanding the materials characterization is very hard, and you don't have you don't have the engineering group at MIT. Yeah, maybe at MIT a little bit, but you just don't have that as part of the production life cycle.
Well, I'd like to throw something in too. This is Carl. One thing that's changed a lot since 1989 is that the background of what's known to be true in physics is way, way different. Like, I don't know if you've ever seen a video of a Bose-Einstein condensate, which is kind of the opposite of what Leonard is. But this was a weird science fiction, mathematical extrapolation that nobody really ever expected to see in real life. But a few years after the Leonard demonstration. That was, seen with the naked eye, and many other weird effects of quantum mechanics, quantum strangeness that was controversial among physicists in 1989 is now part of your cell phone and you use it every day. So, and the other thing is we've got a lot of nanotechnology, and we understand that machines can be atoms in size and do crazy things and things at high energy. I remember seeing the matchbox size X-ray generator at UCLA that Seth Putterman's lab has, where they take sound waves and turn them into X-rays using a crystal. And that's halfway to fusion, by the way, if you can make high energy X-rays from sound. So, just the number of other things that start to make it look like this insane observation actually is matched by reality in a lot more dimensions today than it was in 1989. That's very comforting.
Yeah, and I mean, I think Marie and I are constantly looking for, has anybody really successfully productized this so that it actually hits home with people? Like, is it Brillouin? Is there some example where people can say, hey, I actually have a space heater is there
And I would say
anything like
the
that in the
answer
world?
to that is a frustrating no at the moment, but I expect that to change. And I do feel like high temperature superconductors were a controversial observation, I think, until you could buy them in Edmund Scientific and take them home and watch this little disk levitating. And you could either say it was levitating because of the powers of Satan, or you've got a high temperature superconductor. So people did believe once they could buy a little useless sample. And I think the same will be true for Leonard when we have the tiny demo that you can buy. Anybody who says otherwise is silly.
I'll make a comment on that, actually, because there was some recent news that researchers have produced a room temperature superconductor that was announced may have been a couple days ago. They announced this. Placing the material inside 2 diamond anvils and squeezing it, and it's somewhat surprising. I mean, I think it's been. I think what people may not realize is that there are literally thousands of papers on high temperature superconductivity. Maybe there's like 50, some crazy number.
But
Maybe
those
as
are
many
like
as there
at
are.
very, very high temperatures and pressures, right, that we normally can't access.
No, absolutely. No, what I'm trying to get at, absolutely. What I'm trying to get at is that there's the volume of scientific work to get to this point has just been enormous. Just enormous. I mean, if you say, hey, I want to work in the field of high temperature superconductivity, you're never gonna know everything going on in the whole field. It's just way too big. One of my advisors at Chicago was working in this field, and you have chemists, physicists, material scientists, just so many people working on it. Compared to LINR, which is really quite minuscule. I mean, you don't have thousands. These thousands upon thousands of papers published every year. So just the volume of people working in the field on high temperature superconductivity is just, and we don't really understand why it works. We have some ideas, and some of these ideas have led to the development of new materials. Like there has been an interplay between theory and experiment, which appears to be paying off. But I just wanted to comment on that the volume of work that's gone into it has just been orders of magnitude larger than what we see in LINR.
Yeah, that's a great point. I know that most of you are not scientists or engineers in this room, but this is just a peek into what it takes to get a new scientific discovery to make it out and to make it useful. Like, we still haven't seen this being used in daily life yet, but hopefully one day it will appear. There are many of you who have not had a chance yet to ask any questions. Would love to hear questions. No question is stupid. This is a difficult topic, so You know, like if you go to the conference and someone were to ask you a question in this field, what would you like to be? What type of knowledge would you like to be armed with?
I think I just wanted to comment on the last discussion really quick. I remember reading, it was the book that Carl, you lent me. It was the one with the green battery on there. I think it was like cold fusion. But I read through it, and one of the things that they were talking about was I think there was like a standardized process or a piece of equipment that generally the community uses. I think it's like a tabletop one, and but nobody's ever, I guess nobody has standardized or created or commercialized one. But it would be really useful if the whole, if the whole community had one. And I just think like, if this is the wild west of, what we think of real magic, shouldn't there be like a body or something that kind of trails, these innovations and then standardizes those the things that are true that we find, or is it, I don't know anything about the, IP and how things
So
are standardized and things like this, but yeah, I'm really fascinated about the whole like
okay, yeah.
physics. I just started reading into it, so it blows my mind, Charles. By the way, so
I'm sorry. Say again.
No, like you were just saying, it was it's just so vast, and like I just started reading into it like a couple weeks ago, and like it's just blowing my mind. It's just like never ending. So yeah, I agree. I just want to say.
Yeah, this is the daily life of many scientists who will never see their faces. Yeah, I mean, this is kind of a normal day for a lot of people. The main thing that we want to prevent is to have good science sort of blockaded because of some weird philosophical view on, hey, this is BS or something like that. And so this is one of those cases where there was good science. So
yeah. Well, the big problem with this field is that physics is a science led by mathematicians lately. I mean, it wasn't back in the 40s, but physics usually proceeds by people coming up with a theory that suggests reality might be slightly different than what we think, and then they build some apparatus to test the theory. And then either they have to make another theory, or they get choice between two theories. And with Lehner or high temperature superconductors, nobody thinks any of the theories is satisfactory. And there's no way to extrapolate from theory to experiment. Instead, and this is how it was when they were inventing thermodynamics, the steam engine and all other kinds of engines depend on the science of thermodynamics. But science didn't help that grow at all. All that happened is a whole bunch of engineers had logbooks, and they recorded their observations about how steam engines worked. And then somebody did a curve fit to the curves in the logbooks, and that was thermodynamics. And so it wasn't at all guided by theory, but the theory grew from the observation. And currently, physics is really unhappy with that. Chemistry is super okay with that. That's the way things are supposed to work in biology or chemistry. But when you use the word fusion, suddenly the physicists get to run the show, and they are more biased by mathematics. In fact, most physicists don't do experiments at all. They just noodle around with math. There's nothing wrong with being a mathematician, but if you do defy the real world, then you're not a scientist. You still could be a really good mathematician. But in order to be a scientist, in my view, you have to pay attention to the real world. And sure, try to wrap math around it. But you're not free to create castles in the sky the way a mathematician can.
as an engineer who's married to a scientist, this is the argument I make all the time on decision making.
What's the argument, Richard?
I don't know, like let's say something happens and I go, oh, okay. My wife as a scientist, her general question is like, wait, why did that happen? I don't know, but it happened. We have to deal with it. We have to deal with what's in front of us. We just observed it. We just observed it happening, and we have to sort of make a practical decision.
I consider physicists famous for not believing what they see with their own eyes if they don't have the calculus to back it up.
Fundamental reasons why me and my wife get into arguments.
Can I just follow that up? So I'm not in this space. I just kind of dove right into it. And so I said, you know what, let me go ahead and I'm going to take one of Stacy's articles, post it to Reddit, the nuclear subreddit where people talk about stuff. And I started to, like kind of go back and forth with, I guess, what seemed to be like, I don't know, scientists. And, I've learned that, people see it a different way, and I think others see it another way also. But from what I was learning, I'm learning their point of view too, and they're saying like, what are we working on here? It's the physics and deuterium and I think it was like the isolated. I'm still learning here.
It's okay, Randy. I mean,
are you talking about lattice confinement?
Lattice confinement, yeah, lattice
There you
confinement.
go.
Yeah, thanks, Stacy. It was from your article, by the way, that I learned that. So I had a conversation or e-conversation with someone online about lattice confinement, and they completely do not believe in it. And they're backing it up with all these facts and, these references and things. And basically, I think the idea was from their point of view is, you can't get any net energy from the kinetic energy that's being made because you got to consider like converting that. Like, how does it, what goes into the conversion? And,
yep. Welcome to the internet. No, it's not.
That's not. But that's a really healthy debate, and you want people to come back at you with all those kind of objections. Some will be objecting on practical grounds, some on theoretical grounds. But, in my view, science has to explain reality, and any observation needs to be explainable by science. And but repeatable observations get a lot more credit than momentary observations. And so the trouble with cold fusion has always been making the observations repeatable enough that people are obligated to pay attention to them. And we're getting there, so that's good. I think Brillouin and some of the other companies have demos that are repeatable enough that it's impossible to ignore them. So.
And Randy, Marie, and I can send you some links to the work that has been published by a scientist who's been doing lattice confinement work with NASA.
I'm really.
So you'll be equipped.
Yeah.
Now I'll know what to say. But I really didn't know what to say in response to that. I'm like, well, he's kind of right. I mean,
you don't. I wouldn't try to respond.
I would.
You don't have a problem. Charles, please.
I mean, I can comment on this coming from the theoretical chemistry and physics background, having worked with both fields. There's a very famous electrical engineer at Caltech. Frank probably knows him, Carver Mead, who has said that most of this past century's developments in condensed matter physics have come from the engineering side. People are manufacturing advanced materials, and those materials are, from those materials we learn, like things like the metal insulator transition, which was missed for a long time by theoretical physicists. Theoretical physics has, because large parts of theoretical physics have become a type of mathematical philosophy. And these guys are very difficult to deal with because they are, it's absolutely the case. I mean, even if you do actual physics, they can't really go there are certain schools that think in a certain way. And if you look at theoretical chemistry, it's very different because it's a computational field. You're looking at the equations and you're trying to solve them numerically, almost the way someone in engineering physics would. If you're building a radar system, a complex radar system, or an electrical engineer trying to build a very sophisticated device, you use theory as a way, you build your theories are really computational theories, and you use them to help you design experiments and interpret them. And theoretical physicists don't really do that. Like they're not really engineering physicists. They're not theoretical. They work in that world. So it's just not the world they're in. And I think that if you look at the theory behind, I mean, some of the more compelling theories behind LNR, like some of the work that Peter Hagelstein has done. Well, I mean, it's very interesting. He's basically said, look, if you look at relativistic quantum mechanics and you ask what a physicist does, everything's always in the center of mass motion of the particle. If you're in a lattice, there turn out to be lattice contributions, which they never bothered to incorporate. And if you go back and study physics and you look at and rederive these equations, it's actually quite hard. There aren't many people who spent the time to really think carefully about how the equations they use are derived. So, because it just doesn't come up in their day-to-day work. And, there just aren't that many people who know it that well. And so, so I think Carl's right in that sense. When you deal with these guys, they're very arrogant, and they have a very fixed set of tools that they use, even in the mathematics realm.
Yeah,
And,
I would go further and say that physics is a mathematician's game, and if you want your papers reviewed, you have to be a better mathematician. It doesn't necessarily matter how your work correlates with reality, but more importantly, Charles has helped me understand this a lot. We can set up the equations for how physics really works with quantum color dynamics theory and such. And I only kind of know these things by name. I can't do them. But the point is, you can't run those equations through a computer and generate any useful predictions. So true physics as we understand it is uncomputable. And that's very frustrating to the math nerds who would really like to learn something from their mathematics. They can set up the equations and then they're useless. Same with computing. We can't compute these immensely chaotic structures. So there's no way that you can predict what happens with advanced computation in these quantum mechanics realms either. So now, being a computer scientist, I'm used to Gödel's incompleteness theorem, and I know that not everything that's true is computable. But physicists are still hoping that the universe will be amenable to mathematics, and we know it's not. And it's very frustrating to them. So that's my little diatribe.
I think that's it's very hard. Yeah, it's very hard to get if you look at what people are doing now you'll see Larry talking about doing density functional theory calculations, which is basically, I'm going to solve the Schrodinger equation for a material. And they do this. And they have sort of this parameter space of tunable knobs. And what they do is they get to the material and they know that it's a very classic mathematical theorem. We know that there exists a universal density functional that can describe any electronic system. We just don't know what it is. And so they try to fit it to experiment. And then they have all these little knobs that they turn. And so they'll run these calculations. And they go and they get this software and they just kind of go like this and they run the calculation, they turn the knob, and they can get almost anything out. And if you don't, and it's sort of many of these tools, my advisor used to joke in Chicago. I asked, why don't you produce software for your theories? And then people will run the software, meaning that they'll run it and they'll abuse it. So they do these crazy calculations, and probably 9 out of 10 of this stuff is just they've basically fit the parameters in the computer code to give the result that they want. And so they misuse the numerical, they misuse the computer tools that they have. They misuse the software because they want to produce something. And
I'm not saying it's bad to have theories that are oversimplifications, because only the oversimplifications can actually, you can turn the crank and generate a prediction only if you oversimplify what we know the universe really is. And it's great to be able to simplify a lot of things. It works great for cannonballs, and
Well, the game is to know what simplification to use, That's the whole game. And to know how to, and if you don't know which one to use, or you can't show that it's right, or maybe it works in one case and not another, that's the problem. That's the whole game. And the theoretical physicists, they don't touch this stuff because it's way too complicated for them to.
So Charles, can I ask you, how are these tools used by electrochemists differently?
Well,
chemists are happy to look at an experiment, see what happened, write that down, and call it science. But if you try to do that in physics, they'll say, "Where's your math? We're not publishing this paper."
Let me give a more they do this in AI too. Like, we try to get these papers published in AI machine learning, and they complain that the mathematics isn't rigorous enough. And I go, yeah, they don't. The other stuff works. My stuff works. And we have this debates with, it's the exact same thing, that this mentality has somehow gotten into machine learning. And they write this ridiculous nonsense, this fluff that they produce in AI. And of course, in machine learning, what I would say is the machine learning guys have been doing this. And the AI guys went out and said, we're just going to build AI systems. We don't care why they work. We're just going to build them. And they work great. Nobody knows why they work. They work much better than the machine learning systems of old. And the academics and the universities are still fighting over, they're still quibbling over the theory of why the stuff works. Meanwhile, you have self-driving cars and, self-driving planes. And it's very similar, actually. We used to have a joke that we'd say too much rigor leads to rigor mortis. They just go crazy, and it's like it's all fluff, and that it's very hard to do theory correctly. Well, it's very, very hard because they don't want to test their assumptions. They either make models that are too simple, they're overly simplistic nonsense that you can't apply to anything in the real world, spherical cow models, or they make wild assumptions that they never test. The way an electrochemist uses this stuff would be, I have some molecule and I would like to understand where the charges are distributed in the molecule. Because, I'm trying to produce, I want the molecule to stick to the surface, and I want to get some sort of catalytic reaction. And so I want to understand something about the charge distribution in this molecule that I make, so I can have some understanding of, where I can do different kinds of nucleophilic substitutions or electrophilic additions. And so, Eugene, what they'll do is they'll run one of these calculations, and they'll get a picture of the molecule, and they'll see where the charge density is. And then they can use that to help guide how you might design your experiment. So it's not used it's frequently not used in a quantitative sense. But you can use and they have other theories which are much simpler, curve fitting theories, where they'll try to you try to predict you're trying to predict what is the rate of reaction given a bunch of different chemicals, what rate will be. So you measure a bunch of rates, you do you fit the algorithm to some model, you put a new molecule in, you see what rate it gives out, and you use that as a guess to say whether you should make this or not. It's a much less rigorous approach to doing theory than insisting that everything be derived from first principles, and they're using it in a much more qualitative way.
If you've got a cake, it doesn't matter I don't think it matters what the recipe is, right? You've got a cake.
Excuse me, Randy. Let me just really quickly. Let me quickly interrupt. We've already passed our 1 hour mark for the course. The original intention of the course was to learn about Leonard, but I think we've also learned that academics are probably more dramatic than Hollywood. So are there any questions about Leonard before I let people go from the course? Any Leonard specific questions?
If I understood it correctly, it seems that the most difficult part is to make a very specific materials with indentations or whatever. Is there any 3D printing technology that would actually allow this to be very reproducible made in a more scalable way than just lab made versions of that?
Very good question, which I can't answer.
Well, I think we're at the interface of art and science. If you were to ask people, in certain times in history, how to make Damascus steel or damascene, and it's a basic foundry technique. Those arts were lost, and they came back, and now they're being rediscovered. So, the material science is something that is more of an experimental field rather than a theoretical field, and I think that's where we need more people to be interested in material science to develop those technologies. For instance, in the semiconductor fab area, they have extensive test and evaluation and measurement equipment, and it's all about reproducibility, and the process is about yield. It's not about having a lucky part. And in some areas with Leonard, people have had lucky wires and lucky wafers and lucky experiments where they don't understand because they weren't measuring.
Well, in nanotech, there's lots of room at the bottom. You don't necessarily know what you have, and after you've used it for a while, it's a different thing. Mitchell Schwartz is an example.
And it's everything.
Yeah.
Oh, please.
Mitchell Schwartz is a practicing doctor half-time and cold fusion scientist the other half of the time, and he's quite sure he can always make materials. The trouble is it takes, in the $20,000 to $100,000 range to make one of his parts that performs well. So he doesn't do it that often. I think we need to improve the manufacturability of the experiments, and that's the number one thing.
So you would say, Carl, Schwartz's main barrier is the cost. The way he does things, just too expensive.
Yeah, I mean, he's done quite a few open demos at MIT where they demonstrate the thing working and show how the colorimetry works. But the high performing parts, he's doing some kind of co-deposition with lots of palladium, and it's a lot of tedious work getting the layer distribution. And I don't know all that much about it, but he ends up with a part that looks like a resistor, and it acts like a resistor, except it makes more heat than you put in electricity. Is the nanor. So
right. I mean, I've seen some of his talks, even dating back to 2012, and I was just curious where, if he's got something that's demonstrably works, what the status is. I don't know what the status is, because he has they have a very nice tie-in between his work and what Peter's working on, which is these spin boson models and the boson coupling theory. So they seem to have a nice story where it all ties together, but they seem to be stopped. I didn't know why they were stopped.
Yeah,
like they seem to be stopped on progress, and we're trying to understand. I just don't know what that is, like where the barriers are. And I would imagine if it's really expensive, that would be a challenge.
Yep. If something's expensive and fragile, then you don't do very many experiments. All right. Well, I appreciate everyone's time. It's been a fascinating conversation.
Yeah, thank you.
Thank you.
Any other questions on Leonard? Not the dramatics of academia, but Leonard. No? All right. I mean, everyone's more than welcome to continue to share war stories of physicists and their math in this room. But anyone who was here for Leonard, you're more than welcome to leave now. Thank you for attending.
For having
So,
me.
yeah,
Thank you. Back to work, so it was a really cool discussion.
Cool. Yeah, excellent. All right, Frank, defend yourself as a scientist. Why are you so dramatic, and why have you caused us so much issues?
Frank, what's happening with transmutation?
Transmutation? I mean, that's still going on. It's yeah, isn't that what Brilliant's doing right now?
Is that their radioisotope project?
Yeah, the one they got the guys in Texas to look into.
I'm not aware of that. What, can you tell us more?
Oh, okay. I'm not sure if I'm supposed to talk about it. And then, although Charles and I have seen a preliminary report.
I don't know what we should talk about. What I would say
with
is